to give you a little bit of an overview of SoftMEMS itself, we believe that our mission is to bring MEMS to the mainstream, to help more and more people use MEMS in their systems and to design them using new fabrication processes. And so we're a supplier of CAD tools and design kits for the design and analysis of MEMS. We have two different product lines. One is called MEMS Pro, and that works in conjunction with the Tanner IC design tools. We also have a set of tools called MEMS Explorer, which work with Cadence, Mentor Graphics, Agilent, and AutoCAD. So our company really bridges the world of the, we're sitting right in between the world of EDA tools, which are shown on the left, where we are typically design electronics and do physical design of the electronics. And we're in between the world, which is shown on the right, which is the world of mechanical design tools or finite element tools. So what we help to do is bridge those worlds together, because typically to design a MEMS or a NEMS system requires multiple physical design tools. And as shown on the lower right-hand side, we know that fabrication is very, very important to the design process, and the design of a proper fabrication process is very, very important. So we have very strong links in our tools to a variety of manufacturing partners and MEMS fabrication houses. And these fabrication houses could be pure play open foundries, or they could be internal fabrication facilities or university fabs. So what we help to do is help the designers access information about the fabrication partners through our design tools and our design kits and our libraries. And so we'll see a little bit more about that as we go through the tools today. So what I'm going to do is give you an overview of the MEMS Pro tool suite, and I'll also let you know as we go along how the other tool suites on Cadence, Mentor Graphics, Agilent, and AutoCAD, how they're similar to what I'm showing you today. So the first thing I'm going to talk about is our MEMS Pro Basic Suite. And that is a basic package to design MEMS at the physical level. So it includes a full custom mask layout editor, and that's the layout editor LEdit from Tanner Research. If you don't have LEdit, you can get it as part of the SoftMEMS package, or if you do have LEdit, we can just add the MEMS-specific features that SoftMEMS has created on top of it. So some of the features that we supply to you in this tool, the Basic Suite, is MEMS layout libraries, and so we have programmable examples of MEMS structures to help you design your layouts quickly in a programmable way. We also have a tool called EasyMEMS, and EasyMEMS is a tool for automating your MEMS layout. For example, as we'll see later, putting etch holes in structures is an error-prone and tedious process. So we have a tool that works and creates etch holes for you, part of our EasyMEMS tool suite. We also have a three-dimensional modeler, where the three-dimensional model is created automatically from your mask layout and a description of your fabrication process. So we'll talk about that as well. One of the things that's also important that we know is that there are many tools out there that you need to link to. In order to design a MEMS and electronics and packaging for a MEMS-based system, you have to use more than one set of tools. So we have an output to various 3D simulation packages and other drawing packages. And finally, we have a way to generate the masks that you need to send to your MEMS or IC foundry. So we support both MEMS foundries and also integrated circuit foundries where MEMS may be created either on top or beside or below. So I'll move on and give some specific examples of the features that I've just described. So if we look first at the MEMS Pro LEdit package, as I mentioned, it's a layout editor with MEMS capability. So in other words, you're using a popular IC layout editor, but we've added a lot of MEMS-specific features because MEMS has very specific requirements in order to create MEMS structures that are not typically found in IC design tools. But we wanted to choose a layout editor that it already exists, and we didn't want to reinvent the wheel. So we chose a popular layout editor, LEdit, and added a lot of MEMS-specific features. So one of the things that we've done is we've added a specific tool feature here, which is a toolbar into the basic LEdit interface. So you basically would bring up LEdit, and we've added a toolbar to it. And what our toolbar does is it adds support for curved structures, which are often found in MEMS devices, and also curved features are also found typically in microfluidics layouts. As I mentioned, we also have a set of tools called the Easy MEMS tools, and these automate MEMS-specific tasks, as I mentioned. And the output is, as I described before, we need to send to the fabrication house so we can export GDS, we can export CIF, we can export DXF, and we can also read these formats in. So you can come from other tools into our suite, and you can also export right directly to the foundry. A lot of MEMS foundries are familiar with our tools and take our formats directly. So let's look at the first very specific MEMS features that we've added. We have, as I mentioned, we've added a solid modeling tool into the LEdit layout environment. So as shown here, we have a multi-windowing system where you can have a mask layout that you've drawn in LEdit and various views of the structure in 3 dimensions. We can also take a cross-section of your MEMS device from within the layout editor as well. So you can display your layout, your 3-dimensional model, and your cross-section all within the same tool. And then, of course, you can pop that cross-section output into snapshots for PowerPoint for putting in theses and publications. So in order to go from the 2-dimensional world of layout into the 3-dimensional world, we've got to emulate the fabrication process which was used to create your MEMS device. Because the layouts, the mask layouts, are used as etching masks for a fabrication process. So MEMS Pro allows you to describe the fabrication process sequence, and then the masks are used to etch the various etching steps, and from there we can create a 3-dimensional model. Now MEMS Pro enables you to emulate the fabrication process not only of MEMS, but a variety of other fabrication processes, such as those used in optical fabrication, in microfluidics fabrication, or you can use MEMS Pro to simulate semiconductor fabrication processes as well. So it's not just a MEMS tool. Some of the features that we support are listed on the slide here. We have multiple wafer manipulations. So if you're going to model the creation of multiple wafer devices, including their packaging, you can use our wafer manipulation commands. We have a variety of deposits that mimic different tools that are used in the fab. So depending upon how the tool deposits material, we can emulate the specifics of a given tool. We have a variety of etches, for example, that can be used to describe those etches used in microfluidic etching and isotropic etching for bulk micromachining, and a variety of etches that are used for surface micromachining. We also, as I mentioned, have some semiconductor IC processes like implanting and growing steps that are typically used in IC processes. And then we have things like mechanical polishing and also electroplating, which would be used maybe in a high aspect ratio metal process where we need to electroplate some thick material. Now, the fabrication process editor allows you to easily describe your fabrication process, and what's shown here is a graphical user interface where we can enter the process sequence, and for each step, the specific parameters can be entered on the right-hand side. But if you would like to program the tool, we can also allow you to import and export XML descriptions of the fabrication process, or we also have an output to Excel. So if you'd like to communicate the information between the CAD tool and, say, your fabrication process sequence with the folks that work in the fab, you can perhaps use Excel output to communicate this information. We also have a variety of tools to document your fabrication process, and we can automatically produce process cross-sections with a step-by-step display so that you can see for your device each of the fabrication steps as you go along in the fabrication sequence. So basically, the way the 3D tool works is we would have a layout as shown in the upper left. We take the fabrication process description for the process. In this case, we've shown an optical process, and then we create automatically the view of the device that was shown in layout. And so this tool helps us to be able to understand fabrication effects, and also it allows us to be able to create a very good three-dimensional model that we can then use in further processing for doing things like finite element analysis. As I mentioned here, for example, we're showing that we can go from a layout, which is shown on the bottom, to a three-dimensional model, to a tool like ANSYS. Because typically the layouts are done in ADA tools, as we mentioned, Tanner and Cadence and Agilent, but typically MEMS do need to be analyzed in 3 dimensions. So we have outputs that go directly to popular finite element simulators. And we use the native formats of these finite element simulators. So for example, if you're using ANSYS, we can go directly into ANSYS using their native formats, which is APDL. Or if you're going into tools like SolidWorks, we have a standard format called SAT, which SolidWorks can read. So we have very tool-specific formats that we can write for finite element tools, such as COMSOL or ANSYS, and we have very general formats for reading into tools like Pro-E and SolidWorks. Some of the time when we create a solid model of a device, it's a very complicated process, and we may have a lot of topography or a lot of holes, which may cause problems to finite element simulators. Typically, a complicated geometry will cause a lot of meshing points and will cause a lot of computation points to be spent in doing the finite element analysis. So what we have added to our tool is the ability to defeature or to simplify a three-dimensional model before it goes to the finite element tool. So on the left-hand side, I've shown a little model of an accelerometer, which has etching holes, which are necessary for the fabrication process. And then on the right-hand side, you can see a model which we've removed the holes automatically. So you can have 2 versions of your model. One will show the true fabrication process, and the other one can be a simplified view of the model that can then be sent to the finite element tool. And both of those model descriptions are contained within the same tool, so that you can be sure that what you're modeling came from the mask layout that you're going to fabricate, and what you're sending to your finite element tool is something that you are sure has a connection to the layout. Another tool that we have in our MEMS Pro tool suite is a tool that enables you to add your boundary conditions directly on your mask layout instead of putting them on in your finite element tool. The idea here is that you would really like to have your mask representation be the one that contains all of the information about your design. And so if you change your mask layout, you can change the boundary conditions automatically along with the mask layout. So by putting the boundary conditions in with the same tool that we create the mask layout, we're sure that we know exactly what the conditions are that we want to simulate, and they correspond exactly to the mask layout that we're going to send to fabrication. A lot of times what happens is that some folks may create a mask layout in a layout tool, and then in a finite element tool they recreate their design, and the 2 designs may or may not represent the same device. So with our tools from SoftMEMS, we're sure that we can go from layout to finite element simulation all with a single database with a single set of boundary conditions and material properties. So what I've described so far was our basic suite, and that is a tool suite that allows you to create your mask layouts, create 3-dimensional models, and then send them to a finite element tool or to be fabricated at the fabrication house. So what I'm going to describe a little bit now is our next tool that is called our verification suite. So this is another tool to which we've added a couple of capabilities that will help you to verify that the design that you have created with the first tool is correct. So what we're adding now is the ability to check design rules and also to extract a netlist that describes your device design. So we'll describe a little bit more the individual features of this tool. So the first part of this tool that I'd like to describe is the design rule checker. Now, if we're going to do design rule checking in MEMS, we have to do a little bit more complicated checking than what's done in the typical integrated circuit design rule checker. So we still have to check things like the manufacturing rules, the spacing, the surround, the size rules, but we've also got to be compatible and check carefully layout that has curves and all-angle shapes. And a lot of IC design rule checkers can't handle those types of geometries. We also need to support MEMS context-sensitive rules. In other words, if depending upon how a MEMS structure is going to be used, it may have a different design rule, which is typically not the case in an IC design tool suite. So for example, I might need to check the number of etch holes per area on a plate if that plate is going to be part of a movable structure. Whereas if the plate is a part of a capacitor, I don't need to check that rule. So we have to know the context under which a rule is to be checked in order to be able to apply the right rule. In MEMS, we also have to support device-specific rules. So depending upon the application of the structure, we may be checking a different rule. So for example, if we may need to check that the stator is present over a ground plane on a motor. So with the MEMS Pro design tool suite, we've added some additional capabilities in order to check these additional MEMS rules that, as I mentioned, we don't have to take care of in the IC world. We're starting to see some more context-specific rules in the IC world, but in MEMS, it's a requirement. I'd like to key in on one of the most popular design rule checks that we supply, which is the capability of being able to check whether a plate is releasable or not. In MEMS, we have to add etching holes at a regular distance so that a plate or movable structure can be released. So we have a design rule check that enables you to discover whether your device will be released or not, given the foundry design rules. So we can then mark, as shown on the slide, the unreleased regions. And these will be marked on an error layer, so you can go back and add more holes to your structure if it's needed. So that was our next tool suite, which adds the verification of MEMS structures to the basic suite. And now I'd like to describe the next package, which is called our design suite. And this adds to the verification suite the capability of being able to simulate electronics, MEMS, and packaging together. And the idea is that typically MEMS are not designed in a vacuum. We typically have electronics driving them, we have electronics sensing them, and also simulating packaging effects is very, very important so that we can really optimize and design the overall system. So what we've done in this other suite is to be able to add the capability of doing the MEMS and IC simulation together. So what's shown here is our suite where we can create schematic symbols for both the MEMS and the electronics and simulate them together. What I've shown is a schematic of a Q-controlled resonator device where we have created schematic objects for the MEMS devices, and we can hook them together to the electronics. In order to do that, we have added the capability of modeling the MEMS devices with a variety of different modeling techniques. We can create equivalent circuits where we model the MEMS device as using the same objects that we would use in an IC simulator. We can also model the MEMS devices with analytical equations or with table-based models. In order to be able to simulate all of the types of analyses that we'd like to do in the electronics world, we have to create models for the MEMS that are usable in transient, DC, and AC analysis. We also support the parametric analysis, and we describe our models with a variety of languages. So we can output our models in SPICE, in MATLAB, and in high-level languages like Verilog 8. You can also create your own user-defined descriptions if you like. And this will allow you then to do things like optimization. We can optimize our systems if we have good models, and we can then answer questions, which would be how to create the mask layout to achieve a given optimization target. For example, in this case, I've shown that we want to simulate a resonance frequency of 30 kilohertz, and we'd like to know what are the design parameters to achieve this goal. And finally, another important simulation that we want to do for our MEMS and our electronics devices is statistical analysis. And so we can incorporate statistical information from foundries into our models and then do things like Monte Carlo and yield analysis. And this enables you to be able to create better structures that are more manufacturable, in the sense that MEMS right now does not have as high a yield as are typically observed in the integrated circuit world. So we really need to understand and be able to simulate the effects of fabrication variations on our MEMS devices. So I hopefully have explained a little bit now about how we can simulate the electronics and the MEMS together. And then a very important issue that we also want to take into account is the fact that we need to simulate the environment along with the MEMS device. So we need to take into account the fact that we may have a MEMS structure, but then after the structure itself has been created in mask layout, we need to take into account that we may be adding parasitics by routing wires and putting other structures next to our MEMS. So with the MEMS Pro tool suite, we can do things like re-simulate our devices after they've been routed or put together with their packaging. And so just to I'm going to go ahead and skip forward a little bit to give you a little bit of a summary. Let me find summing up how the tools fit together. We've created a set of libraries for you so that you can both access popular structures in our layout libraries and also in our schematics. So for each device that you are going to create with the MEMS Pro tool suite, we can describe it in a parameterized way. So for example, here on the upper left, I've shown you some schematic symbols that we've created in a library, and also on the lower right, we have programmable structures that we have created mask layout representations. And so these representations are tied together in our library so that you can both simulate them with your electronics and then create the structures themselves in the layout. So I think I'd like to just skip to our end here and summarize some of the things that our tools can do. We can help you visualize what your devices will look like in 3D after they're fabricated. Our 3D models can be used for 3D analysis to figure out device behavior. We can take the output of the 3D simulations and make models that can be used to simulate electronics and MEMS. And we can also model the packages used to enclose the MEMS and look at how the packaging affects the MEMS. And as I mentioned before, very importantly, we can optimize system performance if we have good models, and we can also analyze statistically how the behavior of the fabrication process variations will affect our performance. And so I hope I've given you a little bit of an overview of how the MEMS Pro tool suite can go from simulating things like fabrication effects through design rule checking and verifying the MEMS structures, and also talked a little bit about how we can simulate electronics and MEMS together so that you can look and take an overall system approach to design. And so now I'd like to take some questions if you have any. My understanding is at the top of your little application area, there's a question and answer area that you can ask questions. So I'd like to open up to questions now. Are there any questions in the audience? I think if you have a question, you'll need to type it by in the question and answers area. I think that you can't do audio with this application, as I understand it. I have to go over here. Okay, well, it sounds like we don't have any questions. My understanding is that we did have a question about what's the difference between our tool and some of our competitors. The difference between our tool and our competitors is that we have taken an approach where we are linking MEMS-specific features to CAD tools that already existed. When we first came out with our tools in 1997, we realized that people had existing environments. They had Cadence, they had Tanner, they also had tools like ANSYS. So the MEMS Pro tool suite was from the very beginning designed to work with other tools. We did not create our own layout editor, for example. So I think one of the strengths of the MEMS Pro tool suite is that we exist and we link to a number of tools that are out there already that are being used for other design purposes. And the other strength of the SoftMEMS tools is that we really understand design. The flow that is used in creating MEMS Pro was that folks are doing custom design. There's not a particular design flow in MEMS. We have to allow for the creativity and understanding that tools are going to be used in a variety of ways. And the other strength that we have is we really understand the design process. A lot of the people on our team are former designers, and they know how devices are designed in the real world. And so it's not that we're just experts in analyzing and simulating, we're experts in the area of design, which is a creative process. So I think that's the big strength that we have at SoftMEMS, is we understand the